Okay, let me continue now. For the transfer function, we can also use another comment. As you know, transfer function gives the relation between the output and input. Okay. For example, if we have gs as 2s plus 6 over by s cube 5s square 9s plus 5. If we have this kind of function, we can easily represent as, for this function, numerator should be 2 and 6 and denominator 1, 5, 9 and 5. Those are coefficients as you see here. Then we can express this function, this transfer function, with the TF command, numerator and denominator. Okay, TF command create a transfer function by using the numerator and denominator. Let's do this in here. The numerator is 2 and 6. Denominator will be 1, 5, 9 and 5. So we can create the transfer function by using the TF numerator and denominator as like that. As you see here, we can easily get the transfer function as you see here. You can do the same operation by using another form. First of all, we have to, let's be clear before, clear all and CLC, and then first of all we have to define S as the symbol of the transfer function. Okay, to do this, S will be equal to TF. What is the symbol for this transfer function? S. Okay, then now we know this, S is a symbol of the transfer function. Then we can write the same transfer function directly as 2 times s plus 6 over by s cube plus 5 times s square plus 9s plus 5. As you see here, the same transfer function can be built by using this form. What else? We have also some useful commands regarding the transfer function. For example, if you want to find zeros or poles of a transfer function, we have some kind of commands. For example, if we get zeros for any function, we will use 0 for what? Which function? G. G is the last transfer function expression as you see here. By using this command, we can get easily zeros of this function. What is the zeros? 2s plus 6 will be equal to 0. Then you can get the 0 as minus 3. Also, we can find the poles of the transfer function as the pole command for the same transfer function as like that. What is the pole? Minus 2 plus j, minus 2 minus j. Those are complex conjugate poles. And the final roots minus 1. Okay. We can easily find the poles and zeros of the transfer function by using the 0 and pole commands. Okay, the other command is pzmap. By using this command, we can mark the zeros and poles of the system on the plane. Let's do this on the S-plane, the real axis and imaginary axis. Pzmap for the G. Yes, as you see here, poles and zeros are marked on the plane. Maybe you can use the grid. Yes, we have a pole at -1, as you see here, -1 on the real axis. Where is it? Here. We have -2, -j, -2, as you see, -j here. This is the second pole. And the first pole, -2 and +j. As you see here, we have another pole, -2 +j. As you see here, if you click on this pole, you can also, the specification belongs to the pole. For example, for this pole, as you see, damping 0.894, overshoot for the percentage 0.18, and the same information as you see here. Frequency is the natural frequency of course. This is another useful comment for the control theory. We can also express the transfer function by using the ZPK comment. If you know for any transfer function poles and zeros, you can express, for example, for this function, as you know, we have the zeros and poles. So 0 will be -3 for this function. What about poles? Poles are equal to -1, we have, -2 +j, we have, and -2 -j. Those are poles for us for the same transfer function. And also for this function we have a gain. What is the gain for this function? First of all, we have to get 2 parentheses on the numerator, so we can get, maybe I can write here, yes, this is the transfer function, sorry, s2s plus 6 over by s cube 5s square 9s and 5. If you want to get gain for this function, we have to get the higher order component of the numerator as 1. So we have to take 2 parentheses here, s plus 3, as the same way, then denominator should be 1, the higher component, s cube 5s square 9s plus 5. So this is the k, which is gain for us. Okay, then we can write the k as 2 for this function. Then we can express this transfer function by using the ZPK command, zeros, poles, and gain. Just like that. Then you can easily express this function in this form. As you see here, those are the 0 and the complex conjugate poles, and -1 real axis pole. That's all. If we have the same RLC circuit with the same input, ET, R, L, and C, with the same parameter, R is 1, L is 0.5, and C is 0.2. Henry and ohm, of course. And ET is the same, -2 UT. Let's get the initial condition, EC0 as 0, and the first derivative of it, also is 0. Assuming the initial condition as 0, let's get the transfer function for this circuit. Again, in here we have a circuit. Et is equal to R times C dEct over dt. The output again ECT, assume that, plus LC dEct d square ECT over dt square plus ECT. Let's get the Laplace transform of it. Minus 2 over S is equal to RC is 0.2 S ECS plus 0.1 S squared ECS plus ECS. Yes. Maybe we can use here US because we want to get transfer function. Okay, so US is equal to, let's get ECS parenthesis 0.1 S squared plus 0.2 S plus 1. Transfer function of it, GS ECS over US will be 1 over 0.1 S squared plus 0.2 S plus 1. This is the transfer function. Now let's do this on the Simulink part, on the Matlab environment. Okay, to use Simulink, as you see here, we have an icon. We have to click on it, and then we used a blank model here. By using this platform, we can also express the physical elements or physical components on it. In here we have a library. Okay, in this library you can use any needed expression. For example, we have to express the transfer function. To do this, in the continuous part, as you see, we have some blocks here. For example, in here, this is a transfer function block. We can use it for this function. Okay. Also, we need an input. The input for us step, as you know. In the source part, we have also step function, as you see. Okay, to see the output, we need a scope. We will use in sync part scope. Okay, first of all, we have to define the transfer function. Maybe we can get it here. And this is, yes, this is the transfer function to need to draw. As you see here, numerator is 1, denominator 0.1, 0.2, and 1. That's all. This is the transfer function which we want to solve now. Yes, for this question, the input is minus 2 ut. So the step function can be arranged as minus 2. Which time, as you know, step function start from the 0. Okay, step time should be 0 for this reason. And we apply the input of this transfer function, and the output will be ECS, as you see here. Then we can see on this scope to this expression. Now let's see it. in here, as you know, the initial condition is 0. So system will start from the 0 and decrease until this point, and then settle to the -2, which is output for us. Input for us. Okay, this is the same function. Maybe we can do the same operation in here. G is equal to 1 over 0.1 s squared plus 0.2 times s plus 1. So what is the input? Input is -2s, so YEC will be equal to G times -2 over s. Maybe we can show it. As you see here, this is the output EC. So we can draw this function. First of all, we get the time response of it. Inverse Laplace of EC will be I Laplace of EC. First of all, we have to define S as a symbol. Then we can show the GS as like that, and then we can express EC, and then we can get the inverse Laplace of it. Okay, let's draw this function according to the, yes, first of all, maybe we can define this function as like that. Plot T for this. We have to use vectorial product also. Yes, we can use guidelines as like that. As you see here, those are similar, right? Maybe we can change this function by changing the solver, because in here in Simulink we will do all of this operation in this platform by using a solver. Okay, you can change the solver as this part: solver selection, type variable step, and solver automatic solver selection. Maybe we can change it ODE 23 TB. Let's simulate again. Yes, now as you see, those are the same. What if we established the circuit real on this platform? What will be happen? What will happen? If I established this circuit to here, what will be happen? Yes, to do this, first of all, we have to use a toolbox, Simscape, and we can use electrical, maybe. Yes, we can use foundation library and then electrical. In here we have some electrical elements. Okay, we have resistor here, inductor here, and where is the capacitor? Here. Yes. We need a power source, DC voltage source here. Okay, we need also sensor here, voltage sensor. Yes. Let's build this function, this circuit here. Please do yourself on your PC. We need also a converter, PC converter. Yes. To convert the signal according to this scope. Okay, we use it because of this. Yes, we want to show this signal on this scope, so we have to change the number of the inputs as like that. Now, as you see, we have 3 input for this scope. PS Simulink converter. Okay, we have to use PS Simulink converter to get this signal to the scope. Let me change the parameter value. R is equal to 1. Okay. What is the L? L is for this circuit 0.5. 0.5. Okay. What about the C value? 0.2. 0.2. That's all. What is the input voltage for this question? -2. Because -2 UT. Okay. What else? Also, we want to show the signal together. How can we do it? We have to use MUX. MUX means multiplexer. You know from the logic circuit. This is a MUX. An input here and an input here. We will use together. Okay, what else? If we have a problem, it will see when we run it. Let's try it. Okay, what is the wrong? We have to use solver configuration block. Okay, let me use it. Solver configuration. Yes. For this toolbox, we have to use also solver configuration block. Yes. Let's try again. Yes. What is problem here? Explicit solver and model. Okay, let's do this. None. Apply and okay. Then we try again. Linear algebra error. Fix it. None, yes. We have already do it. Yes, what should be linear algebra? Iteration matrix. I don't think. Maybe we should use current. Where is the library? Yes, library, sources here, and yes, we have to use reference. Let's try it again. I guess. Yes. As you see here, this is the transfer function belongs to this RLC circuit. Okay. Then it is the real RLC circuit. As you see here, the output of it will be the same. Okay. We can also show the common window output. They are the same. And the third one, these are plotted on this figure. They are crossed, as you see. As I said before, transfer function represent the real systems. How can we find the transfer function? First of all, we have to model the related system. And then we get the differential equations. After we get, we have to transform into the Laplace domain. Then we will do some algebraic manipulation. Then you can get the time response of this function. In here, first of all, where is it? Sorry about it. First of all, we get the, sorry, where is it? Yes. First of all, we get the differential equation as you see here. Then we get the Laplace transform of it. And finally, we get transfer function of this system. By writing on this block this transfer function and applying the 2 minus 2 ut, we can get the time response of this function on this scope. And we're curious about the if we build an RLC circuit with the same parameter, what is the result? Okay, compared it, then we showed it, we saw it, all of them are the same. Okay.